Okay, I want you to picture this right now. You are sitting in the exam hall. The invigilator says, you may begin, and the clock starts ticking. You have exactly 90 minutes. 90 minutes to take absolutely everything you've learned over the past 2 years and prove it on paper. This isn't just another mock test, right? This is the championship final of your Cambridge computer science journey. Maybe you started your path a few years ago with syllabus code 0417 or 0478. Maybe you battled your way through 0983, 0984, or even 2210. But all of that, all of those foundational years, they were just the qualifiers. This is the big league. This is the Cambridge International AS and A-Level syllabus code 9618. And today, we are hyper-focusing on a topic that appears in absolutely every single examination series for 9618, mastering Boolean Algebra basic laws and rules. We're going to look at actual past paper architectures, including some seriously challenging logic circuits from both legacy and modern papers. And we're going to build your ultimate game plan for exam victory. We are going to completely transform the way you approach these exams. We're moving away from that sheer, heart-pounding panic, and we're moving toward a systematic, step-by-step strategy that literally guarantees maximum marks. So take a breath, get focused, because your 90 minutes to glory starts right now.
So, let's start with the big question. Why do so many students struggle when applying Boolean concepts to unfamiliar contexts? To really understand this, we need to look at two contrasting student personas that Cambridge principal examiners see year after year. Let's call them Alex and Sam. Now, we all know an Alex, right? Alex is an incredibly hard worker. Alex memorizes raw computer science facts for hours. Ask Alex to list every single Boolean law, De Morgan's, commutative, distributive, associative, you name it, and they'll recite them perfectly. But here's the problem. There is absolutely no analytical depth. When faced with a complex, unfamiliar logic circuit in the exam, Alex just writes a massive wall of text. They literally just list the laws without actually using them to simplify the expression. Then, on the other end of the spectrum, we have Sam. Now, Sam actually understands the underlying math. Sam gets it. But Sam always rushes and completely ignores the command word requirements. If the Cambridge exam paper says evaluate, Sam just describes. If the question asks to simplify, Sam jumps straight to the final Boolean expression in their head, writes it down, and shows absolutely zero working out. Now picture their flawed answers side by side on the desk. They are just covered in red pen marks from the examiners. This perfectly highlights the massive, massive tension between superficial breadth, just knowing the facts, and analytical depth, actually proving how they work. You see, you cannot just know the facts anymore. At the 9618 level, you have to know how to play the game.
All right, so how do we fix this? Here is our exact game plan for this explainer. First, we are going to lock down the core theoretical foundations. Second, we'll break down the technical methodology, the exact process you need. Third, we are going to reveal the top examiner warnings straight from the grading room. And finally, we'll tackle evaluative algorithm strategies to make sure you secure those absolute top-tier marks. Let's jump straight into Section 1, Core Theoretical Foundations. This is all about building the structural architecture of your answer. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so the theoretical architecture of Boolean algebra doesn't just exist in a vacuum. Examiners construct these exam questions using very precise definitions, causal relationships, and cross-topic connections. When you move up into the AS and A-Level 9618 syllabus, Cambridge examiners aren't just checking if you've read the textbook. They want to see systematic analysis. They want to see that you fundamentally understand how a mathematical simplification in a Boolean expression directly affects the physical hardware of a logic circuit. Look closely at the three-column table we're showing here. This is crucial. It brilliantly illustrates how the exam's assessment objectives target distinct cognitive domains. In column 1, we have knowledge and understanding. Honestly, this is simply stating a Boolean rule, like A and A equals A. It is the absolute baseline. It might get you a single mark. In column 2, we have application. This means taking that rule and using it to simplify a small, obvious part of a given circuit. But column 3 is analysis, and let me tell you, this is where the top grades live.
This requires logical, structured, step-by-step reasoning. It means taking a massive, unsimplified Boolean expression from a completely unfamiliar context, maybe a factory automation system or a complex security grid, breaking it down and mathematically proving why your simplified version is logically equivalent to the original. Top marks literally require you to escalate your thinking through these three specific cognitive domains.
And this brings us to the ultimate comparison: superficial breadth versus analytical depth. Remember Alex from earlier? Alex had superficial breadth. To avoid being like Alex, we're going to introduce a framework that top-tier students use to ensure they hit that analytical depth every single time. It's called the Peel framework. You might have heard of this in other subjects, but it is an absolute game changer for computer science extended responses. Peel stands for point, evidence, explanation, link. When you are writing an extended response about a Boolean algebra optimization, you don't just write a paragraph of text. You make a point, for instance, explicitly identifying that De Morgan's law can be applied to a specific gate. Then you provide evidence. You actually write out the exact part of the equation you're modifying. Next is the explanation, writing out the mathematical steps of the conversion, showing your logic, and finally the link, connecting it all back to how this specific change simplifies the overall circuit design or reduces the logic gate count. Principal examiner reports for 9618 clearly, explicitly state that candidates who use this kind of structured, evidence-based reasoning achieve significantly higher marks. When you compare a superficial list of laws to an answer that actually follows Peel, systematically breaking down the logic, the analytical depth wins every single time, no contest.
All right, moving on to Section 2, the technical methodology. This is where we get into the mechanics of the exam. Let's talk about the method mark strategy.
If there's only one concept you take away from this entire phase of the explainer, please let it be the method mark strategy. Listen to me carefully. In Cambridge Computer Science, examiners award marks for the process, not just the final answer. Let me say that again. Even if your final Boolean simplification is 100% perfectly correct, if you skip the intermediate steps, if you pull a SAM and rush to the end, you will lose the majority of the marks. You must literally prove your workflow to the person marking your paper. This is where our definitive 5-step procedural framework comes into play. Step 1. Deconstruct the question. Get your pen out and physically highlight the command words. Are you being asked to simplify, evaluate, or draw? They all mean very different things. Step 2. Extract relevant data. Pull out the exact Boolean expression or the specific truth table inputs you actually need, ignoring the distractors. Step 3. Select your analytical framework. Decide right then and there which Boolean laws are needed first. Step 4. Execute with clear notation. This is a big one. You have to use the correct symbols for and, or, not, and XOR exactly as specified by the Cambridge syllabus. Don't invent your own notation. Step 5. Present with correct terminology. Walk the examiner through your logical steps clearly and cleanly. Applying the specific 5-step framework blueprint is exactly how you transform those examiner red marks into green check marks.
Let's put this into practice. I want you to imagine you are in the exam right now. You flip the page, and you are presented with a massive, complex binary representation, a huge truth table with 4 different inputs. You've got a 60-second visual countdown timer ticking in your head for this mock data scan challenge. Ready? Go. First, extract the core trend. You scan that table. Where are the outputs exactly equal to 1? You pull those out because this forms your initial sum of products expression. Next, perform your calculations. You apply your Boolean algebra rules, maybe grouping terms, applying the distributive law, eliminating redundant variables. You are showing every single step. Finally, you draw evidence-based conclusions. You state conclusively that your new simplified circuit will produce the exact same truth table outputs as the original unsimplified version, but with fewer logic gates. That right there, that is what rigorous data interpretation looks like in practice, and that is what gets you a perfect score on a high-mark question.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSEs to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
Welcome back. Let's transition right into Section 3, Top Examiner Warnings. We are going to look at the insider secrets straight from the principal examiner's desk.
So we went incredibly deep into the Cambridge Principal Examiner reports for Boolean Algebra. We analyzed thousands of pages to extract the absolute highest risk errors that candidates make year after year. The examiners report three massive recurring mistakes. First up, confusing cause and effect. Students will often state a Boolean rule beautifully, but they totally fail to show how applying that specific rule actually causes the physical circuit to simplify. Second, forgetting to check boundary conditions and edge cases. What happens to your logic circuit when all inputs are 0? What happens when all inputs are exactly 1? Students routinely forget to test these absolute extremes, and it costs them evaluation marks. Third, answers that are not specific to the context given in the question. If the exam question is explicitly about a security alarm system, your answer should reference the door sensor, the window sensor, and the active alarm state. Do not just give an abstract answer talking about variables A, B, and C. Okay, let's do a quick find the flaw interactive exercise. Imagine a student writes this exact paragraph in their exam. By using De Morgan's law, the equation becomes simpler. We can see that A and B is inverted. This means the system uses fewer gates. Now look at that. Can you spot the flaw? I'll give you a second. So, we went incredibly deep into the Cambridge Principal Examiner reports for Boolean Algebra. We analyzed thousands of pages to extract the absolute highest risk errors that candidates make year after year. The examiners report three massive recurring mistakes. First up, confusing cause and effect. Students will often state a Boolean rule beautifully, but they totally fail to show how applying that specific rule actually causes the physical circuit to simplify. Second, forgetting to check boundary conditions and edge cases. What happens to your logic circuit when all inputs are 0? What happens when all inputs are exactly 1? Students routinely forget to test these absolute extremes, and it costs them evaluation marks. Third, answers that are not specific to the context given in the question. If the exam question is explicitly about a security alarm system, your answer should reference the door sensor, the window sensor, and the active alarm state. Do not just give an abstract answer talking about variables A, B, and C. Okay, let's do a quick find the flaw interactive exercise. Imagine a student writes this exact paragraph in their exam. By using De Morgan's law, the equation becomes simpler. We can see that A and B is inverted. This means the system uses fewer gates. Now, look at that. Can you spot the flaw? I'll give you a second. And this naturally brings us to a massive examiner alert. The principal examiner reports consistently reveal that candidates confuse key terminology. You must make it an absolute, unbreakable rule to always define your terms before using them in extended responses. If you are going to write a paragraph talking about a NAND implementation or converting to canonical form, you need to briefly define what that actually means in the context of your specific answer. A great trick here is to use memory hacks. Create your own mnemonics using the first letters of key terms while you're studying to ensure you don't blank out under the immense pressure of the exam hall. Clarity of terminology is huge. It proves to the examiner that your knowledge is deep, structural, and understood, not just a bunch of memorized guesswork thrown onto the page. We are now entering the final phase of the explainer, Section 4, Evaluative Algorithm Strategies. This is exactly how you secure those top-tier marks. For these final questions on the paper, we're moving way beyond basic algebra and into the higher-order critical analysis required to actually evaluate algorithm quality. Let's contrast two approaches to prove what a top-tier answer looks like. A standard answer, the kind that gets a C grade, focuses only on a single code execution. It basically just says, the code works and produces the right Boolean output. And yeah, that's true, but it's basic. Now, a top-scoring A-star answer, it demonstrates true evaluative thinking. It considers multiple potential solutions. It actively analyzes trade-offs. For example, a top student will explain that while one specific Boolean expression might require fewer physical logic gates, saving hardware space, another expression might actually be faster to execute in a software simulation, thereby improving time complexity. You see the difference? A top candidate acknowledges the limitations of their own solution and justifies every single decision they make with hard evidence. They rigorously check those boundary conditions. They don't just solve the problem, they evaluate the overall quality and efficiency of the solution itself. So here is your ultimate checklist, your blueprint for algorithmic thinking and evaluation. Write this down. First, step-by-step decomposition. Break the massive Boolean problem into smaller, manageable subproblems. Second, appropriate data structure selection. Third, efficient code implementation, because remember, your theoretical Boolean simplification directly translates to much more efficient programming and faster execution times. And finally, rigorous testing against those edge cases we talked about. Remember, practical application of these theoretical rules is what actually develops your essential programming skills. And let's do a quick speed writing check here. In the exam, you need a time management matrix. You must allocate your time strictly based on the marks available. Do not spend 20 minutes agonizing over a 3-mark simplification when a massive 10-mark algorithm evaluation is waiting for you on the very next page. You have to be strategic. To summarize our core system for the 96118 exam, always define your terms, always check your boundary conditions, and absolutely secure those method marks by showing every single step of your work. Decode the command words, apply the Peel framework to your extended answers, and manage your time matrix like a pro. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Now, I want to hear directly from you. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep analyzing, keep practicing those past papers, and I will see you in the next explainer.